Thank you. Thank you everyone for having me, and thanks to everyone as organizers. Also, just give me like a heads up when I have like 10 minutes or so.
I'm timing.
Yeah. So what, I got like 25 to talk, 10 for questions, give or take. Sorry. All right. So I'm going to talk about how just regular Dirac semimetals, all your favorite ones, have signatures of higher order topology. And so this work was done in collaboration with a bunch of people. So people who aren't here is Yijun Wang, Jidai, and then also our TQC collaboration. Maya's here, but the other people are still in Europe, maybe Nicholas Princeton right now. And this is also done with Professor Jennifer Cano, who's here, Leslie Shoup, who is here, and Barry and Andre, who were here earlier. So this talk is structured as follows. First, I'm just going to give a brief introduction on nodal semimetals and symmetries and topology. We don't have to do too much of it because there's a lot of people who covered this earlier. But I'm going to focus just on Dirac and Weil semimetals a little bit in detail and talk about how they have sort of different versions of surface states and how you can understand them sort of tuning or pumping relations. And I'm going to use that to motivate a discussion that's a little bit technical compared to the other stuff that's a little more materials-based of 2D phases with intrinsic corner modes, and how you can go between things like insulators with quantized quadrupole moments to what's called fragile topological insulators, as Eslam talked about, and how they relate to more familiar things such as 2D topological insulators, Doppel and crystalline insulators. And using that, I'm going to build back up to 3D and show how you can find semimetals that have hinge states, including some very common and recognizable semimetals. So to begin, a nodal semimetal is something where in the bulk I have some set of bands, and they only touch at a series of points. So it's not like they're touching at lines or planes. I just have a Fermi surface that's characterized by a few number of band touching points. So depending on the dispersion and topological character of those points, I can classify them, or I can give some naming scheme to them. So people call the points in tandem arsenide Weil points. They call the points in cadmium arsenide Dirac points. And then there are these other ones that don't fit neatly in the paradigm. So in these like B20 silicides, like rhodium silicides that people talked about before, we call them unconventional, or people just kind of still call them new fermions from the original paper title. And so for this talk, I'm going to focus on Dirac and Weil semimetals and sort of what's different about them. And so just before I dive into any theory, I just want to establish some terminology. And so any touching point in a crystal where the bands meet is protected from being gapped out by some combination of symmetry and topology. So from the symmetry side, I have translation symmetry that prevents the Braun zone from being backfolded and hybridizing anything. And then I also have crystal symmetries. And so anything that's only unitary symmetries, I call these the universal representations, and they have simultaneously valid eigenvalues. And then if I start adding anti-unitary symmetries, which for our purposes will mostly be T-symmetry, and then implicitly sometimes some magnetic symmetries, then I form co-representations by pairing things, like with complex conjugate eigenvalues. And in addition to that, there's also nodal touching points like Weil points, where they go beyond representation theory. So just by some loop or sphere invariant, I can show that I can't open up a gap even though I've reduced the crystal symmetry and all the bands are labeled with the same eigenvalues or lack thereof. And so on the symmetry side, this sort of topological quantum chemistry framework captures everything in the first class. For the second class, you have to do some additional analysis to determine what's going on. So focusing on Dirac and Weil semimetals, so we're going to call everything that's twofold degenerate with linear dispersion a Weil point, and these things do not need any symmetry besides translation. So as we saw earlier in the week, a charge density wave can gap them out, but if they're isolated momentum space and uncoupled, I can't add a term to gap them, I can just move them around and tilt them. Conversely, Dirac points are fourfold degenerate, they have linear dispersion, and I'm not going to distinguish between whether the bands are like this or whether they're crossed a little bit, I just care about the nodal point. And this point is protected from being gapped out by some additional constraints beyond the Weil points. Specifically for the ones in this talk, I'm going to care about things that have high fold rotation symmetry, so n is greater than 2. But there's also Dirac points where you use some sort of complicated non-Smorvig symmetry to get Dirac points pinned at the high symmetry points. So people call these Dirac and Weil points because if you have this nice isotropic energy theory, it looks like the Dirac and Weil equations. But we shouldn't take this analogy to high energy physics too seriously, because the symmetries of particles in high energy physics are not the same as the low energy theories of crystals. And so for the purpose of this talk, I'm going to restrict myself to Dirac semimetals that, while they may have the same Hamiltonian as something that looks like the Dirac equation, I'm going to enforce crystal symmetries that are only derived from these space group symmetries of crystalline solids. And so if I look on the surfaces, Dirac and Weil semimetals are similar in the fact that they have arc-like surface states, typically. But those surface states are very different in their topological character and properties. So both can be detected with STM and ARPES. But in Weil semimetals, no matter sort of how I treat the surface, I'm going to see these Fermi arcs. They may have a different connectivity if I add sort of atoms to induce some surface Lifshitz transition or something. But in the Dirac semimetals, while there are sometimes topological surface states, there's also these larger arc-like states that can be removed by adding bulk or surface potentials. And so one of the outstanding questions was, is there anything topological about Dirac points themselves? And if there is, what does it have to do with these surface states? So after I get through all the theory, I'll revisit these surface states and show you what they do have to do with an intrinsic notion of topology. And so one way to understand what's going on is to think of my semimetal as a series of 2D slices in the Broughton zone, where the Hamiltonian of that slice is undergoing some deformation and eventual phase transition. And so the easiest thing to do is to just start with some semimetal where all the nodal points are separated along the kz direction. So they're either along the same line, the kz, kx equals ky equals 0 axis, or they're separated, but there's still some descent relation. So the Weil semimetal, what you can show is that as I track 2D planes with increasing kz, then these planes, in the absence of any other symmetry, correspond to either trivial or Chern insulators. And so the quantum critical point, where I close a gap in 2D and go between a trivial and a Chern insulator, is captured in 3D by the Weil point. And on the planes that are equivalent to the Chern insulator, I have chiral surface states that are equivalent to the surface states of this Chern insulator. So I have these Fermi arcs, and the Fermi arcs at each kz are like the chiral surface states of a quantum Hall. Conversely, in a Dirac semimetal, people have looked at try to come up with these descent relations as well, but they got kind of stuck on the high symmetry planes. So for a long time, we only knew what to do with planes that had Chern insulating phases without time reversal symmetry, or with time reversal symmetry, some strong 2D Ti or TCI phase. So you could take a Dirac semimetal and say, okay, at kz equals 0, I have something that's like a 2D Ti or a TCI. At kz equals pi, I do not have that, and so I have what I call a topological Dirac semimetal, where it's some kind of obstructed pumping process between a 2D Ti and a 2D trivial insulator. But then that leaves you to say things like, this configuration of Dirac points is a trivial or normal Dirac semimetal. And this distinction is not satisfying in the sense that I'm completely ignoring everything between the two planes. It's not really controlled. But we can overcome this because, in 2019, we know about other 2D topological phases beyond Chern insulators and 2D TIs and TCIs. And so specifically, in recent years, it's been discovered that there are 2D topological phases with intrinsic corner modes. And these phases come in many varieties, but for the purposes of this talk, because everyone's most familiar with it, and because it lends itself nicely to Dirac semimetals, I'm going to restrict focus to quantized quadrupole insulators, but there are other examples with different rotation symmetries. And so the quadrupole insulator was first proposed by Vladimir Benalcazar, Andre, and Taylor Hughes in this model that I'll get to that's a little bit complicated and involves sort of spinless electrons and threaded flux. And it's distinguished by having some bulk topological property that's called a nested Berry phase that I won't get into too much. But spectroscopically, if I were to calculate the model on sort of a very symmetric open boundary, I find that it either has 4 mid-gap states, or if I break particle hole symmetry, it has this sort of imbalance in the number of states above and below the gap, which basically is the definition of what's called a filling anomaly. And due to the properties of this model, it's been not to date realized in a solid-state system, other than predicted to be observable in some form in the 3D semimetals that we're talking about. Although a phononic version was realized in Sebastian Huber's lab shortly after this proposal. So one of the reasons that this model is difficult to connect to solid-state materials is because its construction relies on sort of contrasting notions of some things acting like the electrons are spinful and some properties acting like the electrons are spinless. So in the model, I have 4 sites that in some unit cell, and I place spinless electrons on each site, and I tune the hopping so it looks kind of like they're in the center. But then I thread a pi flux through each of these plaquettes, and so the dashed lines are the ones where I make the gauge, so these get a -1, and I make it C4 symmetric. And if I do this, and I enforce the symmetries that are required, so I have 4-fold rotation and optionally mirror reflection, then I find that while the electrons are spinless, the symmetries act like the electrons are spin full. The mirror is anti-commute, and everything, like C4 to the 4th and mirror squared, is -1. And so if I were to try to connect this to some solid-state system with the eye towards predicting something else in Dirac semimetals, I don't really know what to do with this. So when I started this project, one of the first things was, is there any other way to get a 2D phase with corner modes, and a 2D phase with a quantized quadrupole moment, without relying on threaded flux and having spin-full electrons? And so to do that, because we were focusing on things with 0D boundary states, which sort of look like the solitons of the SSH chain, the idea was to kind of try to build a higher order version of the SSH chain, but using topological quantum chemistry, so like a controlled sense of atomic orbitals, eigenvalues, 1A functions, things like that. And so, as an analogy, I'll start by discussing the SSH chain in 1D and then show how this gives an alternative, basically interpretation of the quadrupole phase in 2D. So the SSH chain, one formulation of it is I place, I don't have time reversal symmetry, and I place a single s and a single p orbital at the center of a unit cell, or the edge here of the unit cell of a 1D chain. And I just make it periodic, and I have nothing else in the unit cell. And so if I have weak coupling, then I have some kind of almost flat S band, and I'll call that occupied. And I have some unoccupied P band, and so I just have electrons and atoms sitting here and nothing going on here. And so if our per unit cell were to calculate the polarization just by counting the charges, I would say that I don't have any polarization. And now what I can do is I can invert bands at the gamma point, and so I'm bringing down one state from the P band and bringing up the S band. And then what I can do is in a symmetric manner slide out 1A orbitals, and then I'm free to send one back away to the valence band or conduction band and have just a single occupied electronic state that's not lying where it started. So I have an uncovered atom here and an electron sitting here. And then if I calculate the polarization per unit cell, then I get that I have an E/2 dipole moment. And so these two phases are distinguished by their multipole moment, and they're sort of topologically as distinct, though they're trivial in some sense because they don't have winding and they're inherently linearizable. And so the idea is to try and play the same game in 2D. So I take the symmetries of the quadrupole, which basically form this magnetic 2D, magnetic wallpaper group. So it has the symmetries of this sort of, I can imagine there's some background distribution of magnetic charges that lives here, and they have the swirling pattern. So I have C4 and mirror symmetry, but no time reversal. And so I can place 2 spinful s and 2 spinful d orbitals at the corner. And then it turns out, by adding just symmetry-allowed coupling, I can reproduce the corner spectrum and the nested vary phase of the BBH model by just tracking these symmetries and using these orbitals. And in fact, what you can show is that in a particular limit, this model that you would generate is unitarily equivalent to the BBH model. So it's just a re-embedding of the quadrupole model, but using only spin-full electrons and no magnetic flux. And so the way it works is the same as the SSH chain. I can start with 2 occupied S bands. So here I'm enforcing an additional magnetic symmetry, so the bands in this picture are doubly degenerate. And so I have 2 occupied S bands living at the corner of the unit cell. And I have, as defined on the right over here, and I have 2 unoccupied D bands. And so if I were to look at where the 1A centers and atoms live, everything's on top of each other, and I calculate the multipole moments, and I find that I don't have any quadrupole moment. And then I can invert bands and open up an insulating gap at the gamma point, and that allows me to bring 2 valence and 2 conduction binary orbitals together, and I can slide them out in a mirror and C4 symmetric manner till they live in the center of the unit cell, and then I can throw 2 of them back up to the conduction manifold and realize a symmetric insulator again. But here, if I calculate the quadrupole moment, I get the QXY mod E Z/2, which is the same value from the BBH quadrupole. But what's nice about this model is it lets me also play with time reversal and crystal symmetries in a more controllable manner. And so specifically, I can add terms that force the bulk gap open while allowing me to restore time reversal symmetry. And so what you find is that if I keep the quadrupole gap open, and I restore time reversal symmetry without closing the bulk gap, then the edge gap closes, and I realize a mirror-turned 2 topological crystalline insulator. But since MZ is not a symmetry of the quadrupole, I can also break MZ and do the same process. And so I can connect the quadrupole gap to some other phase with all the quadrupole symmetries, T symmetry, and no mirror. And I get the same winding Wannier spectrum, but I don't get edge states. And so what's strange is I've connected the quadrupole to something with no edge states, and I haven't closed the bulk gap, but now it looks like it's not Wannierizable. And so the punchline here is sort of the same as what showed up in Eslam's talk. This is an example of a fragile topological phase. The 2 bands are not Wannierizable, but if I add extra bands, they become Wannierizable. And one way to see this is if I take the previous sort of pattern of sliding Wannier centers, it relied on the intermediate positions between the corner and the center of the cell having singly degenerate orbitals, and that's obstructed from happening by time reversal symmetry. So I can slide 4 out with the crystal symmetries, but I can't slide 4 out with crystal symmetries and time reversal. And what's unique about this fragile phase is it carries the same eigenvalues as just a regular band sitting elsewhere in the unit cell. Most of the fragile phases discovered to date can be expressed as the difference of 2 atomic insulators. So if I write the eigenvalues, I get some minus sign somewhere, and that's sort of an indicator that I have fragile bands. Here, that doesn't work. Everything reduces to just a band, and I have to have either some a priori knowledge that I started with bands at Wannier centers somewhere in the unit cell, or I calculate some Wilson loop and see that it winds, or I fail to make Wannier functions. And what's interesting about this is because I have not closed a bulk or edge gap, then I can connect the corner spectra of the fragile phase to that of the quadrupole. And so what happens here is kind of interesting. As I restore time reversal symmetry, I know that at the end, I have to have Kramers pairs of corner states. But when I get there, they're not half filled. Because what happens is in the quadrupole, I have some average half filling of the corner states. So I have maybe 2 electrons for these 4 states. But as I restore time reversal symmetry and tune towards the fragile phase, I float up 4 fully filled states, and I realize these Kramers pairs of fractionally charged states that have the same charges modulo E as those of the quadrupole. So this is an example of a fragile phase with topological corner modes, and I can add trivial bands. So this is a fragile phase that at half filling, so valence and conduction modes are fragile, exhibits the same quadrupole moment as some obstructed atomic limit at some with other bands at a different filling, so here 3/4. And so I have about 7 minutes, right? 7, 6? Okay, so I'll go through this part a little quickly. So basically to understand this, you want to understand why does this specific 2D TCI phase allow it to gap to fragile and allow it to gap to quadrupole, with an eye on what does this have to do with 3D Dirac semimetals. And so to explain this, what we can do is think of, I have a 2D TCI, which is sort of like the sum of 2 2D TIs. And so what I can do is take a 2D TI with the symmetries of the quadrupole, place it on a disk, and I can analytically solve the Jacobi-Rebbe theory and some nested Jacobi-Rebbe theories, and then break particle hole symmetry. And I can ask, given all the symmetry allowed mass terms for different 2D TIs with these symmetries, so 2D TIs with different eigenvalues and the same symmetries, what kind of corner spectrum emerges? And so for a 2D TI with different C4Z eigenvalues, I find that I get an angular momentum 2 plus 4n set of corner modes. So I get 4 plus 8n corner modes, and at half filling, even if I break particle hole symmetry, they always carry a quadrupole moment. But if I have just S and P orbitals, even if it's C4Z symmetric, I get some trivial arrangement of corner modes. And so the punchline, the upshot, is that this 2D TCI is not the sum of 2 of the same 2D TIs. It's a sum of a 2D TI that would carry a quadrupole moment if I gapped it magnetically while keeping C4, and a 2D TI that carries a trivial quadrupole moment. And you can show this just by adding up the bands that contribute to them and seeing the eigenvalues are the same, that they're equivalent. And so with all this machinery established, I can now build a model of the 3D semimetal and track as a function of KZ what's going on specifically as if I'm tuning the gap in my model and the symmetries between the quadrupole and the TCI phases and the various things with and without time reversal symmetry. So I start with my model in the 2D TCI phase. I break time reversal without closing a gap. So I know that these planes over here are quadrupoles. And then I invert bands, close a gap, and I get this 3D Dirac point. And up here, everything is trivial magnetic and then trivial time reversal symmetric. And so on the surface spectrum, I see the TCI surface states, and I see sort of gapped Fermi arcs like those of a Dirac metal. But in the hinge spectrum, I see these flat band-like surface states that come from the Dirac points and connect to the hinge projection of the TCI surface state. And so this is a higher order topological semimetal. But also, it's like a regular Dirac semimetal. So this model isn't really fancy or anything like that, and the K.B theory is literally the same as cadmium arsenide. So either we're completely missing something, or just there's a whole bunch of topological, higher order Dirac semimetals, and maybe they're all higher order topological. And that's really the point of the talk. And so what we find is that condensed matter Dirac points are higher order topological, naturally. They have associated hinge states that come from the rotation symmetries that enforce them, at least the band inversion one. For the purposes of this paper and talk, we focused on the C4 ones because they have this connection to the quadrupole. But in preliminary work, it's quite clear that this applies more generally to all the Dirac points that you would find along these high symmetry lines. And so to emphasize this, one thing you can do is you can place different orbitals in the same symmetry. So here I have some Dirac semimetal where I put S and D orbitals, and I get these TCI surface states. This is one from before. And I can put PZ and D orbitals in the same model, and I can get some TI surface states. So these are two differently classified Dirac semimetals, but they have the same number of hinge states. So the important point is this Dirac point gives you 4 hinge states, and they connect to whatever is going on here. But because both 2D TIs and TCIs can gap into corner mode phases with the same quadrupole moment or the same filling anomaly, then different Dirac semimetals with the same Dirac points will have the same hinge spectrum near the Dirac point. But this also motivates or allows us to introduce a new kind of Dirac semimetal. And so specifically, I can break MZ and have a non-centrosymmetric Dirac semimetal where at no point the edge gap closes. So this corresponds to the complete absence of surface states. So I can have a Dirac semimetal where I start from a trivial insulator, go to a trivial magnetic insulator, go to Dirac point, go to a quadrupole, go to a fragile phase with fractionally charged corner modes, go back to a quadrupole, and then go to a Dirac point, a trivial insulator. And so here, the surface spectrum is completely gapped, but the hinge spectrum shows one pair of half-filled hinge states, one pair of fully filled, or one set, so 4 and 4 of fully filled hinge states, meeting in this Kramers pair of fractionally charged hinge states. So we call this a fragile topological Dirac semimetal because the bands that are inverted, if they were separated from all the bands in the material, would be fragile just by the nature of the eigenvalues and symmetries. However, of course, in a real material, this is some obstructed atomic limit physics. I'm not trying to claim that this differentiates between fragile and atomic limits. And so this allows us, finally, to conclude what is the origin of the Dirac Fermi arcs and what they have to do with regular and higher order topology. And so in the quadrupole, the edges each carry a keep C4 symmetry and anomalous half of the dipole moment of the SSH chain, where the signs of that half are exchanged by C4 symmetry. And this is reminiscent of what occurs in TIs, so in higher order TIs and crystalline TIs. So in crystalline TIs, there's some anomalous surface phase that's derived from a gapless phase. So here I could think that I have a 2D TI with a single Dirac cone, and I'm gapping it with a different mass on the quadrupole. And so to form a Hadi, I'm taking a 3D TI or TCI, and I'm gapping the 2-fold or 4-fold Dirac masses to realize different surfaces, and the domain walls are what forms the hinge states. And so, for example, in a 3D TI, I can magnetically gap a single Dirac cone. And in a 3D Hadi, I can magnetically gap two Dirac cones or one 4-fold Dirac cone. And in a Dirac semimetal, I can gap the Fermi arcs. And so there's a sense in which the gapped bands on the surfaces capture this anomalous half-integer phase, but there's also nothing that controls the number of gapped bands. So I can float them around, I can pull extra bands. So there's nothing topological about the number of Dirac cones I see. So sometimes I can say this is related to fermion doubling, and I can count the number of Dirac cones and tell you, oh, this is the surface of a Hadi. But it's not controlled. You have to order like express some order of limits with spin orbit coupling or something like that. So anyway, these criterion can be applied to search for these hinge states in real materials, and it turns out that all you need to look for are basically Dirac points along lines of form M symmetry. They all satisfy the criterion. And as I said, there's other criterion, so it basically, just for focusing on the ones that come from the quadrupole, I get this very large list of space groups and very large list of Dirac semimetals that have hinge states. And if we expand it to other states of the corner modes, we probably get the rest of them. And so sure enough, as said before, because we have the same K dot P theory of cadmium arsenide, so that begs the question, does cadmium arsenide have hinge states? And indeed, since Zijun was one of the people who first worked on cadmium arsenide, we just took his original model and calculated hinge states, and indeed cadmium arsenide has hinge states. So cadmium arsenide is a high order Dirac semimetal. And so we also calculated a bunch of other ones, including with some Urichern Dirac semimetal. And so we see if you apply an electric field, you can see these fractionally charged corner states at k equals 0. And you can play with this a bit more and get some other versions. So I'll leave up the future directions and take questions. So thank you very much.
Thanks for the talk. Are there any questions?
I'll go the end.
Okay. So actually, can you go back to the cadmium arsenide?
Yeah.
So you're saying that the material that the community study a lot is alpha prime cadmium arsenide?
So the room temperature phase is the body centered one is the alpha phase, and the high temperature phase is the alpha double prime. But both phases work.
Okay. So then like what shall we look for? So what kind of experimental signature?
So
for these like a hinge state?
So I mean, you could try to somehow cut a very nice corner and maybe figure out some momentum resolve probe. That sounds really difficult. So we were thinking quantum oscillations might work, because you might see something where you have this sort of different dimensionality. So I have like the Fermi surface has some surface component, some bulk component, and some hinge component. So maybe you could separate them. Because I didn't get to it, but you can also make wild semimetals with coexisting hinge states and Fermi arcs. So we were thinking something for wild semimetals where you could pick out the different pieces. And then there may be something where you can manipulate them. So if I had some polar and phase domains like David has for MOT2, they have some sort of signature of hinge states on sort of what look like crystal defects. And so maybe you can move those around. There's some enhanced density of states that you can pick out.
So if I understand correctly, the reason for the appearance of these unusual hinge states is just that you have in the plane, it's 2D TCI with corner moves.
Yep.
It doesn't matter whether it's fragile, whether it's quadrupole.
Yep.
So what happens if I put in one 2D plane some insulator that doesn't have corner moves, and the other 2D plane a topologically distinct insulator that also doesn't have corner moves, that are just distinguished by the representation? Then you get a transition.
Like you're still comparing it to some cut thing. You're just asking as
yeah, both bands don't have corner moves on the same cut, but they're distinct.
Yeah, so I think this is what Mao and Taylor have, and it's just a form of axion insulator where you have a mix. You have a mix of flat band hinge states and it's a magnetic Hadi that has coexisting flat band or magnetic TCI with coexisting surface Dirac points and flat band like hinge states. But I think it's a strong 3D magnetic phase.
So it's different from so much.
Yeah, I mean it's not. I don't think because no bulk gap close, it's not a semimetal. Like I don't like calling that a higher order.
No, so I'm talking about something different. The
bulk gap I thought you were talking about. You have a bulk gap close.
So the scenario you're talking about is you take two boundary obstructed phases essentially.
Yeah.
And deform between them.
Yeah.
But for example, I could take an atomic insulator and take another atomic insulator where I don't change the wake positions, but I just change the representations.
Oh, I mean then it's also as hinge states. Like I can go between two different. I mean the symmetry indicators tell me the Dilling anomaly, right? So if I close a bulk gap with the semimetal, and if I.
But you can have two non-trivial phases without a filling anomaly. So you can have two distinct TCIs that cannot be deformed to each other, but there is no filling anomaly that tells them apart.
well, we should talk about an example then. Do you know one where I close a bulk gap, change the eigenvalues, and get something with the same corner spectrum?
Yeah, just the corner spectrum is determined by the weak of positions, but then there are symmetry labels. But we can discuss it later.
Yeah.
Discuss it there, so do more other questions.
Yeah.
Raquel, you had one?
I was just going to ask because, so it doesn't seem like the corners, what would happen now if you break the C4 symmetry, right? There's no reason why the hinge modes would disappear. So what would
So if I break C4 symmetry, depending on the details of the phase, I mean, I'm going to open a gap, and then it's going to be some kind of TI, TCI, or nothing, basically, because the hinge modes are flat band. So it's how they can, basically it's like what's going on at k is equals 0 and pi will have like a heavy bearing on what happens when I break C4 symmetry. So it's like it's basically like tracking, like breaking the Dirac point phase
the
transition.
Dirac points would open?
Or, yeah, I mean, unless if you don't get a wild point. Okay, so the Dirac points would open, and I have some insulator, and I can try and figure out, is it a hottie, a TCI, or nothing?
I'm just wondering if you have anything to say about your future work point if enforced Dirac points have hinge states. Do you know anything in this direction already, or it's just...
No.
Oh, okay. That would be I would be very curious about that. Yeah.
No. The materials for enforced Dirac points aren't great, so it wasn't an immediate focus.
No, but I mean, yeah.
Yeah, I mean,
have
that's
some
a major
material
question is
but-
if this is a property of every single Dirac point and every single...
Right, like if it would be a property of that, it would be pretty cool. That's why.
Yeah. We're looking at it.
Okay.
Maybe the last question.
Well, simple. As you said, that there are coexisting hinge and surface states. Experimentally, how do they distinguish it?
Well, that's one of the sort of like prevailing questions. You would either need you need something where you can sort of tell the length and momentum space of everything and where it's localized. I mean, that's difficult. So we proposed quantum oscillations or somehow being able to get some probe that had some KZ, like I had a long rod and I could tell you, but at least in the bulk, there's something you can tell. Like there are places where you have some quadrupole mode and some places where you don't. I don't know if that gives you anything, but I mean, spectroscopically, it's going to be quite difficult, I think. You don't have this, it's not like the hottie where you can throw everything away and just have the hinge states there.
And then let's thank Ben again and move on to the next talk.